of the ear. There's not as much there. In fact, there are even some of the textbooks out there, some of the websites out there don't cover the ear in terms of its histology. If we talk about the structures that are there that you're familiar with, the outside would be the auricle of the ear. We'll talk in embryology about how that develops. That's kind of unique and some of the potential problems that are there. But then you, of course, have what you know is the external auditory meatus, the tube that basically brings the sound waves in here into the middle ear. Now, if we look at it histologically, here would be the opening out here to the right, just barely shown on the screen. It's going to be lined with skin, and there will be hair follicles in here, of course, small hairs that are inside the tympanic membrane there. One thing that you look at here, if you look at this, it looks like apocrine sweat glands, doesn't it? Now, you know you don't have body odor produced in your ear, but you do have earwax. These are modified apocrine sweat glands here that produce the earwax, okay? And so, once again, think about what those apocrine sweat glands look like. Coiled, but very large lumen compared to the epinephrine, had a little tiny lumen. That does look like an apocrine sweat gland modified here to produce earwax. And then if we could go just a little bit here to the left of the screen, we'd see either bone or cartilage depending on how far we are in the external auditory meatus. Now let's talk a little bit about how sound works. That will help us understand the next type of structure here. Back in physics or even high school physical science, you talked about the difference between sound waves and light waves, correct? Sound waves are compression waves, aren't they? They're moving air particles or whatever medium it's passing through. That's why, I grew up on a lake in Central Florida. If there was a power boat on the other side of the lake a mile away and you're underwater, you could hear that prop turning. Sound travels even better through water, even better through the old Western movie, the railroad tracks, so they bent down to listen and see if a train's coming, right? And so it's compression waves coming through. You can feel, if we have music and we've got a good woofer, you can feel those sound waves, can't you? Schools for the deaf, their football teams invented quite a few things. As they're signing their plays, other teams learned to sign and would steal them, so they invented the huddle, believe it or not. The other thing that they did, how do you know? We're going to hike it on 2. How do they know what 2 is? And so what they'd have is a big drum on the sideline, and boom, 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 and they know to go on the second boom because they can feel those sound waves. Well, those sound waves that I'm making with my voice right now, they are coming through your external auditory meatus right here. And as they come through, they're going to pound on your tympanic membrane. The other term for that is the eardrum, correct? All right. Now, you stop at some roadside tourist stand and they're selling a Native American drum. How do they make a drum? They stretch a piece of leather over a ring, typically a hollowed out tree or some type of ring, correct? Well, that's the same thing that we're going to have here, basically, in terms of our tympanic membrane. Okay? We're going to have a piece of cartilage right here. Okay, the annulus fibrocartilaginous, okay, that makes a ring. And then we are going to stretch tissue tight over that ring. Now, as we stretch it tight, we're going to see there's part of the ossicles coming, touching on it. We'll come up to that in just a little bit here. But because we've got something, pressing up on that top membrane there, we've got to have a region which is very tight, pars tensa, and that's really what is going to be vibrating now as the sound waves from my voice come in and hit your eardrum. Okay? But then we've got a region up here that, due to the ossicle pushing up underneath it there, is not very tight at all. That's called the pars flaccida. Okay? And this is what you see when you look into someone's ear with an otoscope. Now, if we look at it, do a cross-section of it, here is that tympanic membrane in cross-section. Here is the malleus, the ossicle that's pressing against it, we can see right there. And looking at this, This is gonna be bone. Telling us that's cartilage. What does that tell us about the individual here? This is a mouse pup, wasn't it? Wasn't an old mouse I got this from, okay? Because it hadn't ossified yet, still got cartilage in it, okay? But if you look here, there are layers that make up that tympanic membrane. It's not just like a piece of leather going across there, it's got different layers to it there. It's got a cuticle layer. This is gonna be the outside, sound waves are coming in from right to left. It's got a cuticle layer. That cuticle layer is hairless, thin, hairless skin, okay? Low power magnification 20, you can't tell that here, but if we went up even to 50, 60 power magnification, you'd see that and be obvious. That's skin, but no hair follicles to it. The next layer in is the intermediate fibrous layer. We just label it with I, and this one is going to have two sublayers to it. You're going to have collagen fibers that are arranged radially like the spokes on a bicycle wheel, and then you're also going to have them arranged in a circular pattern around it. And once again, whenever we see layers and fibers going in different layers, that just gives extra strength to it, right? Gives extra strength in more directions, and that's that tough fibrous collagenous material there is what can be stretched tight and gives that good drum effect here to your tympanic membrane. The inner layer is called the inner mucus layer because it now is going to have a wet epithelial lining to it. Wet epithelium is what we refer to as mucus. It's going to be a simple cuboidal with an thin underlying connective tissue layer of lamina propria there. All right, now, the next thing to talk about then is going to be the ossicles. All right. Ossicles, there are 3 of them here. In just a second. That's not the slide I wanted right there. Sorry, let me go back a slide. Let me go back to the first one to show the ossicles. All right, the ossicles are 3 little bones here in the middle ear. Okay, they are the malleus, the incus, and the stapes. And their job is to amplify those waves. Those sound waves are coming in that I'm speaking right now. They're coming in and they are vibrating your tympanic membrane, beating on it like a drum, but they're only vibrating that tympanic membrane, let's say, as much as a piece of paper, thickness of a piece of paper. They're just barely vibrating. Well, what we need to do is amplify that vibration, okay? Simply a mechanical way of doing it. If I take, once again, we're bringing a lot of physics and physical science into it here. If I take and have my pivot point on this microphone where my fingers are, I can take and barely move one side and the other side moves a whole lot more, doesn't it? Okay, barely move it on the short side here on the pivot point, the long side moves a lot further. That's basically what the malleus, incus, and stapes are doing. They're taking that tiny little vibration that my voice is producing on your tympanic membrane, and they are mechanically amplifying it. Okay? Now, the stapes is going to be sitting on the oval window of the cochlea. And the cochlea we're going to see is a tri-layered compartment, a fluid-filled compartment here. Tri-layered, we look at it there, it kind of looks like a snail. Pointer on it. Okay. Here's the cochlea right here. Kind of looks like a snail. The analogy that I'd use, I meant to grab an extension cord from the garage this morning. I could roll up that extension cord because it's got 2 layers to it basically. 2 wire extension cord, not 3. But then rather than just rolling it flat like you would be on your desk, I kind of have to push pull the middle up or something a little bit here. Okay? We're going to see that in the next image coming up. But basically what we're going to have is we're going to have on the oval window, showing the round window, not showing oval window here, but what we're going to have is you're gonna have that stapes sitting right on the cochlea. Now, that's a fluid-filled compartment. You guys are still familiar, but they were very popularized in college waterbeds. Okay, and if I have my hand on the waterbed and I start doing this, doing CPR in the waterbed, what am I gonna do? I'm gonna create waves in it, aren't I? And that's basically what we're gonna end up doing here within the cochlea. Okay, got this little tiny vibration, the sound waves from my voice hitting on your tympanic membrane. You've got the ossicles then amplifying that tiny vibration, and the end of the ossicles is sitting on the cochlea, giving the cochlea CPR, creating waves inside those fluid compartments. Okay? Now, let's go back and look at it here as, a little bit more detail. All right, here's the idea of the cochlea. It's wrapped around a little spiral, a little projection here of bone. It spirals around it. I like this image and how they, took the microscopic image and put in the spiral case here. So in other words, it's not a flat, like you're coiling up something on your desk. It's three-dimensional in that respect. But the cochlea has three subcompartments to it. Here is one piece of the cochlea. It wraps around, let's say, behind the bone right here, and here's where it comes out on this side, wraps around the front of the cochlea, here's where it's wrapped around to the back again, here's where it's coming to the front, and so on. That's what you're looking at here. And each time we look at that cochlea, there are three compartments to it. There are the scala vestibuli, scala media, and scala tympani. Those are the three openings that we have there. The scala vestibuli is what originates at the oval window. It's filled with the fluid we call perilymph. Scala media is in the middle. And go to the next image here a little bit. Here's scala vestibuli right here. Here's scala media. It's the Reissner's membrane that separates the two. This is going to be filled with not perilymph, but endolymph. They're both water-based, just a little bit different in terms of their ionic makeup. And it is made by a tissue over here on the side called the stria vascularis. You see the stratified squamous epithelium there, highly vascularized underneath in this connective tissue down here, and it makes that, anytime you have a water-based solution, you're making it from plasma. You're going to have a lot of vascularization to that tissue. It contains the organa corti right here, which we're going to come back to in some more detail in our next slide here. And then just below that down here is the scala tympani. It's separated from the scala media by our basilar membrane that part of the organa corti is sitting on right here. All right, the other thing to talk about in here is over here. You look at it, you see some very large cells, don't you? One of the things I've kind of said multiple times through here, you see large cells, what do you think? Neurons. And that's exactly correct. That's your spinal ganglion. That's some of the interneurons or the neurons that are involved in your eighth cranial nerve. Okay? Sense of hearing, vestibulocochlear nerve carried by the eighth cranial nerve. The primary receptory neurons here for the sense of hearing are going to be found right here within that spiral ganglion. All right, let's talk then about the organa corti. Another one of those histology slides, kind of like the retina yesterday, I really like. They have a high resolution, very good image, and they make a drawing directly from that. Cell per cell, it's made to match up to this microscopic image. This is the organa corti, and this is where you get your sense of hearing. Okay, it's resting here, at least partially, on that basilar membrane right here. And then you've got a tectoral membrane right up here. And that tectoral membrane is sitting on top of 1, 2, 3 hair cells, okay? Specifically the outer hair cells. You look at them labeled over here, and they made them yellow over here. All right, now say it's sitting on top of it. I'm gonna say 3/4 of the slides that you make of the ear, and realize this is very expensive slide. It's embedded in, it's a hollow and temporal bone, which is the hardest bone in the body, okay? And so it's not an easy slide to make, to decalcify that bone enough to make that slide and so on. And because of that, I must say about 3/4 of the slides that when I've purchased them in the past, that tectoral membrane is up here waving in the wind like a flag rather than sitting on top of those hair cells. So if you don't see it on top of the hair cells, that's fine, that's just an artifact of the preparation. It is sitting on top of the hair cells. In fact, latest research says it even sits on top of this inner hair cell right here, but I've never seen one showing that, but the latest research says, yes, it's sitting on top of that inner hair cell as well. We just can't make the slide like, realistic enough, in vivo enough to show that, or in situ enough, I guess I should say, to show that. Okay? The inner and outer hair cells here, they are actually your sensory receptors. Okay, here is a hair cell. The hair cell, the hairs on it are stereocilia and then one true kinocilium. Okay? I've seen some sources that will talk about microvilli. Really down here, they're probably short enough to be a microvilli. Here, they're long enough to be short stereocilia. So if they say microvilli instead of stereocilia, don't worry about it. It's just a difference in length, correct? But it's going to have one true stereocilium. And what happens here, if you look, this cell is being cradled here at the end of a dendrite. And when this kinocilium is bent, the cell can detect, is it being bent to the left, is it being bent to the right, is it being bent front, back. It can detect the direction it's being bent and then signal that here through this dendrite to that neuron in that spinal ganglion. Now, remember we're building up waves in here. And basically, a wave, as the wave goes, it's got a crest, and then a trough, crest, and a trough, and so on. And so it doesn't press against the organ of Corti throughout the entire length of the cochlea. Only crest and trough are going to be pressing against that organ of Corti, creating effects on that organ of Corti. Now, here is where it gets confusing. Some textbooks have it caught up. When I was teaching this, 20 years ago, what we always said was that the waves come down and press on this tectoral membrane, which then bends these hair cells. You see they have it drawn touching that inner hair cell as well, and then you detect that as your sense of hearing. And because there's, if it's only, let's say, hitting at the trough, I'm hitting hair cells here, here, and here within that length of that, within the length there of the scala media. On the other hand, what if I've got shorter waves? I'm hitting it more often at different points, aren't I? And so where I'm hitting it within that scala media, that tells me that's different sounds, different intensities I won't go into, but it's kind of simple to understand, isn't it? In terms of generating different wavelengths, will press different organs of Corti in different regions of that cochlea, and that would be interpreted as different sounds. Now, that's how I learned it. What they say today is really the waves are pushing up. It's rather than a trough pushing down on the tectoral membrane here from in scala media, it's scala tympani crest pushing up, pushing these hair cells up against that. Okay? That's what the experts in this area say. Net result, it really doesn't matter. Okay, you're bending the hair cells against the tectoral membrane, correct? If I don't say that, I get questions. I read one place and I'm pushing down on it, the other place I'm pushing up on it. Some textbooks, particularly histology textbooks, haven't caught up with the latest research on it. Okay? Actually, I had students years ago, Dr. Olgan was teaching sense of hearing to the medical students. I believe she still does. I said, Dr. Hill, you got this wrong with Dr. Olgan. So I had to go see Dr. Olgan. He said, oh, the latest research. Okay? Hadn't made it to histology textbooks then. About half or so have it, the latest now.
Yeah.
Okay? But either way, it's sound waves passing through, whether it's really the waves in the scala media or the scala tympani, doesn't matter. Basically, we're gonna be bending these hair cells against the tectoral membranes, and that's how we get our sense of sound. Now, there are some other supportive cells in here. Go back, they're gonna be labeled over here. There are, the hair cells, is really 1, 2, 3, 4 of those in total. You can see them 4 in total labeled here in yellow. There is the outer phalangeal cells, which are the pink supportive cells over here. There is the inner phalangeal cells, which are the supportive cells over here. And then you've got these pillar cells, which help maintain this little structure right here called the tunnel accordion. There's a function to it, different hypotheses of that tunnel and what that allows and so on. I'm not going to go into that, and I'm not up on the latest theory in terms of what that does in terms of your sense of hearing. But those are the supportive cells, my inner and outer phalangeal cells and my pillar cells, and I always think of those as little tiny wedge cells to maintain that tunnel accordion right there. All right, any questions on the sense of hearing? The 8th cranial nerve is the vestibulocochlear nerve, correct? And so now what we need to do then is talk about the other side. Here is the cochlea, right here spiraling. That was all for our sense of hearing. What about all of this over here? Well, we've got 2 sets of things to worry about over here. We've got the very obvious, which are these 3, maybe look like circus rings or a circus ride or something there, the semicircular canals. But we also have 2 structures right here and right here. Those are the utricle and the saccule. And we'll talk about the utricle and the saccule first. These are called the otolith organs. Okay, and what is an otolith? An otolith is little teeny calcium carbonate crystals. Basically, you can think of those as being little tiny rocks. Okay? Used to be an old phrase, an old saying, maybe your grandparents have asked you if you did something dumb, you got rocks in your head or something. Just shake your head, yeah, they're called otoliths, okay? That's basically what those otoliths are. All right, let's talk about, come back to that. Let's talk a little bit about the setup here in terms of the otolith organs. If you take a look, you got an epithelial lining down here. It starts off cuboidal, goes to columnar. I'm not that concerned about that right now. But then you can see, once again, yellow hair cells in here, can't you? Okay, the supporting cells that are in there, we'll just leave them as supporting cells right there. But if we take a look at the hair cells, there's 2 different types. You tell there's 2 different shapes, correct? There are columnar hair cells, and there's what we call goblet hair cells. And I'm not going to go into the different hypothetical functions of those. They're going to function together. We'll describe their function together right here. The cilia on these are embedded within a gelatinous glycoprotein layer. And on top of that glycoprotein layer will be those calcium carbonate crystals that we refer to as otoliths. Okay? The otolith organs here, the utricle and saccule, they're going to tell us about linear acceleration. And it's pretty easy to understand how this works. Pretend you're in your car and you've got little tiny otoliths, maybe bigger otoliths so you can see them sitting on your dashboard. Okay? You're driving down the highway at 60 miles an hour, you hit the brakes real hard because somebody pulls out. What's going to happen to those otolith organs on your dashboard? They're going to roll and go right against your windshield, won't they? Okay? The same thing has happened to these otoliths in your utricle saccule. They're rolling forward at that point in time, and you can detect that as I am decelerating. Okay? If you've got a lot of horsepower in that engine and you have to get somewhere quick, you hit the gas hard so you can accelerate fast, then what's going to happen to those otoliths now? They're going to roll backwards, aren't they? And as they roll backwards, you can detect that as I am now accelerating. Also does the position of the head, because otoliths are going to move when you do this. and when you do this, aren't they? And so, pretty easy to understand how this works. If you got these little hair cells in there, otoliths are going one direction, going the other direction, bending those hair cells, and that's how you can detect position of the head and linear acceleration. Okay? Once again, I think it's fun teaching things that just make sense. Okay? All right, let's move on to those ring structures there. Those are our semicircular canals. Okay? Semicircular canals, we're going to see there's something inside there called the crista ampullaris, which is our sensory organ. But what you can't appreciate here from a drawing is that those three semicircular canals are situated on the X, Y, and Z axis. I mean, X and Y, we've done plenty of graphs for going through high school and all, college, X and Y graphs. Remember when you had to do 3D graphs, you had X, Y, and Z? Okay? These are on the X, Y, and Z planes. All right? Basically, these are going to tell you angular acceleration. Basically, because they're situated in three planes, they can tell me if I am spinning in this direction, if I'm doing somersaults forward, or I'm doing cartwheels side to side. No, I'm not going to illustrate that. Okay? I will not try to illustrate that, but I mean, you get the idea. That tells me if I am turning in any of those three planes. And that's what we're going to be detecting here. How do we do this? Well, if we take a look at this in a little bit more detail, here is our crista ampullaris. Okay? That is our sensory organ, and there's some artifact here in terms of the preparation. Basically, this is sitting down at the base. You have some of these sitting down at the base of each otolith organ, and when you look up here, when there's this portion starting, say, about right here. Looking up around, when you see the epithelium, you see the lighter colored cells in there? Those are hair cells, and you've got to get the idea there's something along the surface here. Well, what you don't get a real good effect here is, here it is in the drawing. This little peninsula of tissue sticking up. Depending on the species, it depends how it sticks up. Does it stick up like just a little mound like this, or is it a big projection sticking up like the last image? But what we lose in the processing is this big glycoprotein layer that we call the cupula. Okay? And if you take a look, here are the hair cells, here are the hairs of those hair cells up within the cupula. Well, if I am, spinning round and round and round like this, take my cup of iced tea here. As I start spinning it round and round and round, eventually that fluid starts spinning, doesn't it? When I initially start spinning the cup, the fluid is not spinning as fast as the cup is it? It takes time for it to catch up there, and that's what's happening here is that fluid starts to go in one direction, and as it moves in a direction, that cupula bends with the fluid. Okay? And as it bends with the fluid, that tells me, hey, I am going in this direction. Not only tells me I'm spinning in that plane, it actually tells me, am I going clockwise or counterclockwise? Okay? Let me ask you this. If I've been spinning, what's going to happen when I stop? The fluid still spins for a little bit. Think if I didn't have all the ice in here, okay? It would stop, it would still spin. I'm spinning. It tells me I'm spinning. What happens when I stop? It's still spinning, but other senses are telling me, no, I'm not spinning, okay? My brain's getting mixed signals, and what happens? I'm dizzy, okay? You ever wondered how a figure skater can spin that many times so fast and stop and there be this graceful move, okay? Where you and I are going to be falling all over ourselves like we're drunk, okay? They basically have trained their body to say, ignore the semicircular canals, pay attention to everything else, I'm not spinning anymore, okay? But that is how that works. And once again, you've got this set up in all three planes there. Whether I'm spinning where I'm going to get dizzy, whether I'm doing somersaults, whether I'm doing cartwheels. I can detect that, can actually detect direction. If you train yourself, you can start determining, you can be in a blindfold and you can determine which direction somebody is spinning you on that laboratory stool or whatever. All right? Any questions on the ear? All right? Promised you a short lecture on that. Normally I would just do lab right now, but I really want to break it up.